Yesterday I sent out the email for anyone who has a unchangeable conflict with the exam tomorrow night. So if you didn't reply, some of you have replied. If you haven't replied, please reply this afternoon. I'll be sending out further emails to those people about rescheduling, like maybe tonight or tomorrow morning. Okay? So please respond, like right after class today if you did not respond to that email. If you have a class till 7:15, you can make the test. If it's on campus, you can make the test. Okay? Because as long as you make it by 7:30, even if you get there a little bit after 7:30, before 7:45, you still have enough time. Okay? So if you can't get there before 7:45, then you have a conflict that we'll need to reschedule for. But if you have a class till 7:15, that's okay. You can take the test at the regular time. All right. Next thing is review. So if you go to exam prep and homework solutions, hopefully you've already started with this. Exam 1 resources. First thing, super important, concepts and skills review outline. Okay? There's nothing on the exam that isn't mentioned there in that outline. Okay? So this is all the most important things that we did. So as you're studying, this is kind of the centerpiece of your studying. You're looking for examples and situations that you can practice, and you're always relating that back to principles on that outline. Figuring out what you're strong at, what you've got down, and what you need more work on. Okay? And again, we're going to be testing your understanding of things, not your ability to do procedures. So make sure you understand. You haven't just learned to do the problems we gave you, but you really understood the important things about those problems that you could transfer that to something else. Apply it to something else. Okay? So they're showing you can see what formulas will be given on the cover page, so then you'll know everything else will be up to you, okay, to know. Here's some extra practice on the most recent stuff, some problems there. I think maybe you're doing some of that in recitation, or if not, it's just good practice for the exam. And then we have solutions. Chapter 1, Chapter 3, Chapter 4 solutions, those are updated to match up with the current text in terms of problem numbers. And so, as you know, we don't spend very much or time at all going over homework problems. So that's for you to dig into those solutions and then come in and get help if you're not understanding something. Okay. So then, what is that's in the exam prep and homework solutions. Lots of resources to help you study. And then, is tomorrow? Do we have a room? Okay, so this is the same place where you're taking the exam tomorrow night. It's from when to when? What's the hour? Yeah, the review. 1 to 4. Okay, so 1 to 4. And that's is that taking over office hours? Like everyone who has office hours there will be there instead. Okay, so for tomorrow afternoon's office hours, any office hours, I will have my regular office hours in my office. But then starting at 1 o'clock to 4, instead of going to the location on the schedule, you can go to Wexler 21, and this is the same place as the exam, so it'd be good just to at least just stop by so you know where you're going tomorrow night. This is in the basement. It's Wexler. Wexler 21. 1 to 4 p.m. is study session. So it's not they're not going to present anything to you like here's an overview of everything we've done so far. It's a study session with the TAs there to help. So 1 to 4 p.m. study session, and then come between 6:15 or 6:15 to 9 is the exam. Wexler used to be called PSA. We're still kind of at the end of the transition here. So that's at the corner of Tyler Mall and the Palm Walk. At the corner of Tyler Mall and the Palm Walk is the Wexler building. That's Physical Science Wing A. Down in the basement is 21. And then from 1 to 4 tomorrow is going to be study session instead of office hours. And then the exam is in that same place. Arrive between 6:15 and 7:30 or 7:45 even. Questions about those logistics? Yes, please. It's handwritten, so you'll have papers in front of you. There's no GC. So yeah, it's designed that you don't. You can bring a handheld calculator. You won't need it for many questions, maybe one or two. You can bring a handheld calculator, but you won't have GC, and we know that in having designed the test. In that way. What's that? Graphing calculator is fine. Yeah. Graphing calculator is fine. Other questions about the exam? Yeah. Hour to hour 15-ish probably, but a lot of you might leave in less than an hour. I don't recommend that. I recommend that you take it slow and think through carefully. You have to read carefully, think through everything really carefully. If you're rushing through and it feels really easy, then you're probably not thinking about it hard enough. Okay, take your time. It's about 25 multiple choice questions. Okay. Gotta know it. So the questions are designed very specifically to see if you know what's up, okay? Not just can you do a few calculations. Yeah. Don't study any differently though. Whatever test you think is the hardest, study it. A format of test you think is the hardest, study like it's like that. It's a challenging test, okay? You gotta know your stuff. Other questions? Other questions? Okay. All right, so again, tomorrow I got normal office hours. Please come find me, okay? I don't talk this loud in office hours, okay? So don't be afraid. I'm a super nice person, okay? And I'm definitely will take as long as you want to answer questions and help you, okay? And then you got the 1 to 4 p.m. Wexler 21. Okay, so let's talk about. So I'm showing a relationship here, and when you look at that blue line, what are you really looking at? How many points? Infinite number of points. When you look at, so your imagination, when you look at any graph, a line or a curve, is that you're looking at a whole slew of points. And each one of those points is showing the simultaneous values of two variables. Okay? And then those variables can change. And as they change together, we get more correspondence points. It would take too long to draw it that way, right? So this is our way of representing that many points. But your imagination, when you see that and you think, just a whole mess of points in a continuous line or curve. All right, so here's an important question. Given a variable x, what's the difference between x and the change in x, dx? So now that we're getting into constant rate of change and getting into these contexts, we know this concept of dx is kind of elusive. We know that there's struggle with it. Okay, so let's talk about that. Right now I have dx set at the value 2.3. So what's the difference between x equals 2.3 and dx equals 2.3? Okay, so I want you guys to talk amongst yourselves. What's the difference between x equals 2.3? What would that mean? And what would dx equals 2.3 mean? Go, talk. Okay, so let's start with dx actually. So this is really the more difficult thing. So let's start with that. So what you imagine, what you maybe should have talked about, or what you should imagine. This is the way we want to think about dx. That dx is a change in x, so a change in x of 2.3. And with that, only that information, that can occur anywhere. It can occur here. A change of x of 2.3. It can occur here. A change of x of 2.3. If all you know is that the change of x is 2.3, it's not attached to any particular value of x. The initial value of x could be anything. All right? So when you were thinking about what dx means, was this your visual image of it? Okay, or you could have thought of that up here starting at the correspondence point. So there's two different ways to represent a dx of 2.3 relative to this relationship, this blue relationship. Okay, so dx just means a change, and that change can start at any value of x. Now, once I pick 5.5 to be the starting value, now the ending value of that change is determined, right? So now if x initial is 5.5, what's x final? 7.8, right? 7.8, okay? But without that information, it can be anywhere. So now what about x equals 2.3? So specifically, x equals 2.3. How is that different than that? Is that mobile? No. So if we want to think of that also as a length, where would that start? X equals 2.3. It would start at 2.3. If we want to think of that as a length, x as a length, it would start at 2.3. Is that right? But it's a quantity, it's an amount, right? So yeah, we think of it as, we say, oh, right here, this is 2.3. Yeah, that's true, but it's still an amount. How do we show it as an amount? No, not a vertical line. Nope. How do we show the value of x equals 2.3? Starting from where? Starting from 2.3? No one's good at it. This is x equals 2.3. It's a quantity measured from 0. Always measured from 0. So if I wanted to show that amount, I'm showing that as a length or as a segment. And that will, if it's x, it will always start from 0. But again, dx can start anywhere. Dx of 2.3 is a change starting from any current value of x. Okay? So we're focusing on x equals 2.3, but if you're talking about a situation, you want to imagine x changing through all its values, right? So for some context or some situation, at some point in time, x takes on the value 0 if that's in the domain. 0, and then 0.1, and then 0.5, and then 1, and then 2. So we think of these situations as dynamic. X increases starting from 0 or starting from whatever lowest value, and it changes through many values. It's a variable. X is a variable, right? So when x is 4, it can be represented this way. At that just we paused time or paused our situation. At the moment x was 4, we could represent it like that. From 0 to 4, okay? Now, all values where x equals 4 is the vertical line through 4, okay? So all points on this graph with an x value of 4 could be, yes, a vertical line. So this could be all points on this graph where x is 4. So it would be the vertical line through 4. Okay. Does that make sense? Okay, and so for our purposes right now, how do we calculate a value of dx? How do we calculate a value of dx? X final minus initial. Final minus initial. So once the final and the initial are given, now our dx is locked in a certain place. But just dx by itself, a value could be anywhere, like I showed you. But once you know either x initial or x final, then it gets locked in. And we pause the situation at that particular starting in any values of x. Okay, so how do we calculate that? We calculate that as x final minus, so dx is x final minus x initial. Okay, so what about dy? So now, given a value of given a certain dx, if x and y are in a constant rate of change relationship, we have dy. So how do you imagine dy? How do you imagine dy in this situation? Tell the person next to you. So now I've shown you a particular dx like this. How do you model on this display? How would you model or imagine dy? Go. Tell the person next to you. Okay, so did you imagine this? Okay, so given in this particular relationship, given this change in x, the change in y could be shown as how much does the y value change as x changes that much from x initial to x final, something like that. Okay, where could we really see that amount? Where could we really see that amount of change? Over at the y-axis, okay? So that's dy. Okay, so here's where we're getting tripped up. So we've got this process that we're learning about finding new correspondence points. We're writing the relationship of a constant rate of change relationship. For our purposes right now, dx we're going to find by, so dx, the change in x, we're going to find by x final minus x initial, or it would just be given. Dx would just be given. But then we've got constant rate of change, so we're going to find dy in a different way. We're not going to say dy equals y final minus y initial, because often we're looking for y final. Okay? Here's an important point. So don't look at that dx equals x final and x initial as, oh, that's my formula. Whenever I have a change, I'm going to use that formula. No, now we've got constant rate of change, so dy we find in a different way, not y final minus y initial. How is it that we find dy? Related to dx. Oh, please know this. You should know this, right? Working on it for two and a half weeks now. dy equals? Yeah. Okay? So, don't just attach onto this formula of x final minus x initial as a change and then apply that to dy. For our purposes right now in the course, we want to find dx as x final minus x initial, and then we want to use constant rate of change to find dy. M dx. We have dx, we've got a constant rate of change, we know that. Given any change in x, the change in y is that m times dx. Does it make sense? So I think that's a big tripping point. It's a lot of students, they just gravitate toward this final minus initial, and so they do that every single time. But oftentimes we're looking for y final. That's what we want. We want y final, so we can't calculate dy that way. So instead, we're going to use this other way. It's that dy is always that constant multiple of dx. But that's if y and x are in a constant rate of change. If y and x have constant rate of change. Okay? And so what would you, based on this picture right here, what would you say is the constant rate? What is the constant rate? Talk to the person next to you. So for this particular relationship that I'm showing in blue, what is the constant rate of change, or can you estimate it? Go. You're not calculating anything. You're estimating based on what you're looking at. You're estimating based on what you're looking at. Okay, so what is the meaning of it? Given any change in x, it's what you would multiply to get the change in y. So it's basically you're comparing changes in y to changes in x. How does the change in y compare to the change in x? What multiple is it? How does any change in y compare to any change in x? And it doesn't matter. I can change dx. I can change the location of our dy and dx, and that relationship holds. How does dy compare to dx? It's about what? What's that? You should think it's about 1/3 of dx. You see, it's about 1/3 as long as dx. Does it matter how big dx is? Small dx, larger dx. It's maintaining this relationship if it's always 1/3 of dx. Does it matter what my x initial is? Does it matter what x initial is? Nope. So no matter what my x initial is, where I am this way, and what my change in x is, dy always ends up being a third of what dx is. So that multiplier is constant. It always is a third. So our constant rate of change is 1/3. Or that's our estimate, right? It's about 1/3 as much. So anytime the change in x stays the same, then the change in y is consistent. It's always 1/3 of that change in x. And then if I can change the change in x too. I can change dx. My dy maintains 1/3 of what dx is. So those are all equivalent to saying that we have constant rate of change. If you apply the same change in x at different x locations, you get the exact same change in y. And if you change the change in x, the change in y is always that same multiple, 1/3 as much as whatever your change in x is. Okay, so this is when we get into these contextual relationships, this is the way we're thinking about constant rate of change. Okay, so let's try something here. Yeah, please. Well, in that question, yeah, for that situation, I mean, that was my question too. Yes, estimate what the value of m was for this. What's that? Yeah, so yeah. So that was my question to you in this particular case, was estimate the value of m. Does it make sense? Okay. All right. So let's look at this here. Don't write this all down. It'll be on the video. So during a basketball game, a camera suspended on a cable begins moving. Okay, inconsistently at first. So you've seen at concerts and sporting events, they hang these cameras up on cables and they fly around and get great views of stuff, right? Okay, so after 2 seconds, after it starts moving after 2 seconds, it starts moving at a constant rate from left to right along the length of the cord. Okay? Let x be the time in seconds since the camera started moving. Y be the camera's distance to the right of the left basket. So we're looking at the cord here. The left basket's over there. The right basket's over here. And so it's that y value is the distance to the right of the left-hand basket. All right, so here's some info. The camera was 1.48 meters to the right of the basket at 3.2 seconds. And then at 5.5 seconds, the camera was 3.97 meters to the right of the basket. Okay, so we want to practice this thing that we were working on Thursday, and hopefully you worked on also in your homework. We want to use that. Let's just remember that process. What was that process we used to find new correspondence points or find the relationship between two constant rate quantities? So what was that first thing we did in that process? Change in x, right? So I'm just going to write out words here, and you take care of the symbols. Change in x. And that we're going to do x final minus x initial, right? Step 2 was change in y. Now, what we were just talking about before is, for our purposes here, we want to use constant rate of change to do that. We don't want to use the same y final minus y initial. To do the change in y, we're going to use constant rate of change, okay? And then the last thing was find final value of y. And we had a way to do that. Now that we have the change in y, we can deduce what the final value of y is given having that change in y. Okay, so I need to take this off. Let's plot those points. So here are those. Okay, so I want you to take 5-10 minutes. See how far you can get through this, okay? See how far you can get through this. Work together. But this is review, okay? This is review. To get started, there's something we need. What do we need to get started? We need the constant rate of change. So let's just, before we do anything, let's get that. How are we going to get that? Right. Yeah. Okay, so because it wasn't moving constantly the first 2 seconds, we have to subtract 2 seconds from both times. Well, right. Yeah, so it's just changing the reference point to the starting point rather than the beginning. But the beginning is time since it started moving. So, okay, and what do we get for that? So we're going to do should have gotten, so change in y would be 3.97 minus over okay, so if you're calculating m, if you're calculating the constant rate, then yeah. So if you're happy to calculate it, we're going to need the change in y however we can get it. Any change in y and a corresponding change in x. So we can get that. And what did you all find for that? .083. Okay, what are the units on that? Meters per second. And what's the meaning of that number? What's the meaning of that number? Tell the person next to you. We're all experts at this. What's the meaning of that number? 1.08 meters per second. Okay, so I heard some good explanations there. Given any time in seconds, the distance is going to move. The change in distance during that change in time in seconds is going to be 1.08 times the change in time, right? So given any change in time, the change in distance in meters will be 1.08 times that change in time. Okay, so now we're interested in how far to the right was the camera, and so how far to the right? What is that asking? The right, it's asking for, gee whiz. That's asking for specifically y what? It's kind of like a y final. Okay, it's kind of like a y final. How far to the right? Because that y value is distance to the right. Okay, at 8 seconds after it started moving. Okay, so at 8 seconds, we're actually looking for what? Something to do with this. Of course, there's a correspondence point for 8 seconds. Something like here. I'm just guessing. I just kind of eyeballing it. Okay, so where that is. So how are we going to find that? We're after this y final. So this is our process, right? So we start with change in x. Well, what change in x are we looking for? We have to decide on a reference point, a starting point. So do we want to choose point 1 or point 2? Doesn't matter. I'll just choose point 2. We can use either one. So let's choose point 2. And what was the coordinates of that point? What did I tell you? Thank you. So the meaning of that point is that at 5.5 seconds, the camera is 3.97 meters to the right of the basket. Okay, so now we've got our reference point. And so even though it's at time 5.5, this is what we're going to call our initial point. So initial point doesn't mean at 0, at x equals 0. So initial point can be any point that we choose. So this is what we're going to call the initial point. This initial point we're calling it's the 5.5, 3.97. And then our final point is the 8, comma, y final, which we're after, right? So that y final is what we're after. So change in x is 8.8 minus 5.5, 2.5. If you use the other point as the initial point, that's perfectly fine. You have a different dx. You'll have a different dx. Okay? And so then here's where we want to do dy, and we don't want to use y final minus y initial because we don't know what y final is. That's what we're trying to find. We're trying to find this new y final here for 8. So instead, we're going to use what? Constant rate of change. We know that any change in y is the constant rate times our change in x. And our change in x is? .083, was it? Change in x is? Anybody got that? 2 point. Let's do 2 decimal places. How about 0.671. 706 is 71, right? To 2 decimal places. All right. What are the units on that? Meters. Right? The change in distance will be meters. All right. So let's just sketch this here. So we got our change in x. And we found that to be 2.5. We just found dy using constant rate of change, mdx, as 2.71. And so then, now we're going to find at 8 seconds, what is our y final? We've got the change, so how do we find the final value of y using the change? Yeah, we started at 3.97 meters. we changed by 2.71. So to get the final location or distance, we're just going to add, right? So it's going to be y initial plus change in y. Should make perfect sense that the final value of a quantity would be where the initial value of it plus how much it changed. That should just make perfect sense. Like that's like the meaning of addition, right? It's just it's a meaning of addition. Tell me what we get when you do that. If you use the other reference point, the other one, 3.2 and 1.48, and you work it through, you should have got the exact same answer. You got a bigger change in y, added to a smaller y initial, you should have gotten the same thing if you started at the other point. Be good to do on your own, just to verify it. Questions on this? Okay, so now, finding the corresponding points one at a time is way too slow. Now we want to write a relationship that gives us every correspondence point, right? Every correspondence point. And that's question 2. Oh, so now let's skip let's just skip right to C. We want the relationship that represents all correspondence points of x and y. All correspondence points of x and y. And to do that, we're going to start with a point. But now it doesn't have a particular x value. I could have drawn it anywhere on the imagined line, right? I could have drawn it anywhere on the imagined line. And what will its coordinates be to represent every and any point? X and y, right? So if it represents any and every correspondence point, then it's variable. They're variables, right? The variables x and y. So and I could have drawn it there. I could have drawn it here, here, here. Doesn't matter. Could have drawn it anywhere. So we're going to do the process again. And then do it 2 ways, right? So do it using this as the reference point, and then do it again using this as the reference point. Write those down. This was 5.5 and what? 3.97. And this was 3.2, 1 point. Thank you. Okay, so we're gonna build this relationship of all correspondence points twice. First starting from 3.2, 1.48, and then starting from 5.5, 3.97, and then we'll get 2 things that look different, but then we're going to show that they're the same. So we're going to do it twice. Draw the pictures to help you. Draw the pictures. When it gets hard, when we start building the calculus from the ground up, starting Thursday, okay? This is what we're going to use to do that. And your way's not going to work, okay? So please don't think to yourself, I'll just do it my way. That will get you in trouble. That will get you in trouble in this course, okay? So first, for the first reference point, change in x. What is the change in x, or dx? So we know we use final value of x minus initial. And what's that for the first reference point? You should have x minus 3.2. Okay, how can I show that? So we'll do this one, and I'll do red here. So we'll do this in red. So x minus 3.2 could be shown like this. Change it actually right like that. X minus 3.2 is our dx. Corresponding change in y. Corresponding change in y. So we know what dx is. We've got the constant rate. Therefore, dy is. You're all thinking it, right? 1.803083 times dx, which is x minus 3.2. Given a change in x, for this, we've got constant rate of change. The change in y will always be 1.083 times that change in x. So finally, y equals 1.48 plus, right, the change in y. Okay, so that looks like this. Then there's our dy, and so we're going to start at 1.48. We're going to change y by that much, and we're going to end up there. And but that point I drew could be any point, right? It could be any point. So then we get this relationship. Okay, other one I'll do in blue. dx equals, what does dx equal? X minus 5.5. How do I draw that? So from here, I draw down like this, right? No, it's going to be horizontal. Horizontal first, independent variable first. So it's going to be like this. Go like this. That's our dx. Okay. There's dx. dy, change in y. M times the change in x. M times the change in x, but x could be anything, right? X could be anything, so we hold on to this expression. And we know x could change, so then dy is defined by 1.083 times x minus 5.5, finally. Then our y equals 3.97 plus the change in y, 1.083 times x minus 5.5. Are they the same or different? Okay. If we do them, so what we're going to do now, so if you multiply this out and you multiply this out, we should get the exact same line. So in this case, so what are we going to have? We're going to have 1.083 times x and then we're going to have negative 3.2 times 1.48 or negative 5.5, sorry, negative 3.2 times 1.083 plus 1.48 will be our constant for that. Or negative 5.5 times 1.083 plus 3.97. We should get the same number both ways, right? So the negative 3.2 times that plus that, or negative 5.5 times the 1.03 plus 3.97 should give the same number in either case. What is it? Do you get that either way you do it? So you should, when you multiply this one out, you should get the constant negative 1.986. Same with this. Okay, so we could write y as that. But there's a problem with this. Not a problem. It still gives us all the correspondence points that we want. But it's less meaningful. Why? So you see this and you say, oh, we just did mx plus b in the end, right? Why didn't we just do that from the beginning? This is like mx plus b, right? What about b? What is b? Is the position after 2 seconds? So no, it's the position, when do you get y equals b? When x equals 0, right? If you put in x equals 0 is when you get this number. Is that meaningful for us in this situation? No, because the constant rate starts at 2. Okay? So let's graph the line. And I can use any form there. So I'll use x minus 3.2 plus 1.48. Now, but I want that for what domain? For what values of x does this make sense? X greater, yeah, greater than or equal to, yes. X greater than or equal to 2. Shouldn't have moved around, sorry. Okay, good enough. All right, so here's the deal. What about this? What's the meaning of B in this situation? Negative 1.986. What was happening before the first 2 seconds from 0 to 2? We don't know. It was moving left, right, speeding up, slowing down. We don't know what it was doing in the first 2 seconds. All we know is that at 2 seconds, it was at this location, and then it started moving constantly across the court. So for our purposes in this context, that B means nothing. It kind of means like where would it have been? It was at a constant rate the whole time, but that's not what happened. Okay, so this negative 1.986b or equal to b is meaningless for our situation, and so it underscores the value of having this form. And are we gonna need this? You got to understand this. That we can just start building this line at a particular point. In this case, 3.2, 1.48. We can start building the line there, and then go from there. We don't care about what happened before. We don't care about the y-intercept. We're going to need that. This is called point-slope form. We've got this point 3.2, comma 1.48. We know the constant rate, so we can start at that 3.2, 1.48, and we can just build it from there. And what's happening before that, x values before that, doesn't matter. Because what we're going to eventually do is we're going to piece a bunch of these together. So when we get to the new piece, we're going to start from the point at the end of the old piece. And we don't care what's already happened. We just start at the new point with a new rate, and we build a new piece. And then we've got a new point at the end of that one. We've got a new rate, and we build a piece from there. That's why we need this. And that's why mx plus b is not helpful. Doesn't make sense. Yeah. Multiply it out. So you can take the red equation and take negative 3.2 times 1.083 plus the 1.48, or you take the blue equation and do negative 5.5 times 1.83 plus the 3.97. So I solved these, I expanded it and added the two constants together, and both of them should be the exact same thing. Okay, does it make sense? Okay, let's do top hat. Top hat.